Hello, my name is Isan Vahidi. I'm postdoc at MIT Concrete Sustainability Hub. And today I'm going to talk about my research, which is about the potential greenhouse gas mitigation solutions in the United States building sector. Okay, so actually we got our idea from this article published in New York Times in 2019, and it's about how to cut US emissions faster. So in this article, the authors just talked about different mitigation solutions around the world. So 7 actually different mitigation solutions around the world, and they evaluated the impact of those mitigation solutions if they are applied in the US in order to reduce the GHG emission from 2018 to 2050. So the first mitigation solution was a British carbon tax similar to British Columbia in Canada. And the second one was New York goal for clean electricity generation. And number 3 was Norway's aggressive electric vehicle incentives. Number 4 was China's efficiency target for different industries such as cement, steel, and petrochemical. Number 5 was California-style energy codes for new buildings. Number 6, Canada's methane rule for oil and gas operations. And number 7, and the last one, was Europe's legislation for phase out of HFCs. So you can see that by applying those 7 mitigation solutions, but after applying all of them, so by 2050, we still have more than 3 gigatons of GHG emission. But the goal based on the Paris Agreement is less than 1.5 gigatons of GHG emissions. So in this study, the main objective was first providing an outlook for the environmental impacts of building as well as concrete in buildings in the US. So in order to reach this goal, so we had several steps. The first step was designing reference building based on regional conditions or climate zones. And then after designing the reference building, we evaluated the energy use phase and also the embodied impacts in those reference buildings. And then we scaled up our analysis from single buildings in a different climate zone to the whole US, considering that we had the total area in the US by 2050. We know about the new buildings, we know about the surviving buildings by 2050. So we considered all of these information. The first step was designing the reference building based on regional conditions. And as we know, we have 2 different building categories. So commercial buildings and residential buildings. In residential buildings, we considered both single-family buildings and multi-family buildings. But in commercial buildings, we have more than 10 different categories in commercial buildings. So we did a clustering analysis, and based on the results of clustering analysis, we considered office buildings and healthcare systems. And then we evaluated different frames. So for example, in the residential buildings, we considered wood frame as well as concrete frame, as well, and also steel frame buildings. So we evaluated all different buildings frame in the US, and you can see that we have 14 different subclimate zones in the US, from zone 1A in Florida, Miami, Florida, to zone 7 in Dulles, Minnesota. We have 14 different climate zones. So we designed 14 different, the reference buildings for the whole US. Okay, for designing reference buildings, we needed to know the code adoptions. So we know that the code adoptions are different based on regions and also based on building types. You will see here, so 2 different code adoptions for residential and commercial buildings. And we all know that, building energy codes get more stringent. So for example, if we have a building code, 2012 building code, if we introduce 2015, the 2015 is more stringent compared to 2012. If we consider an energy efficient building code, for example, in 2018 or 2021, it will be more stringent compared to 2015. So in our study, we had three different energy code adoptions. The baseline was IECC 2009, and then we had IECC 2015. Also, we introduced another energy code adoption. We called it energy efficient, which represents the future energy codes for different buildings in the US. And then we evaluated the energy use phase and also embodied impacts of all buildings. So for energy use phase, we used the BOPT software tool developed by NREL, and then we extracted the bill of materials as the output of the BOPT, and then we used that bill of materials to evaluate the embodied impact using Athena impact estimator for buildings. So this is the sample results for medium-sized offices that we got, similar results for all different building types. So this is the baseline scenario when we have IECC 2009 and without any improvement in the concrete mixes with 0% supplementary cementitious materials, SCM, 0% SCM. So as you can see, we have two different bars. So yellow bars represents the embodied, and also green bars represent use phase. In the next slide, in the next graph, we'll have IECC 2015 and 50% utilization of 50% SCM and CCU CCS, carbon capture utilization and carbon capture storage. You will see that by applying those mitigation solutions, and also by applying more stringent code, by adoption of more stringent code, both embodied and use phase will be reduced in all different 14 subclimate zones. You will see the different subclimate zones from zone 1A in Florida to zone 7 in Dulles, Minnesota. And these are the sample results from all different studies from all different building types. So the next step was evaluating the deviations from the baseline according to alternative scenarios. So we had 6 different mitigation solutions. Improvement in the lighting, improvement in the efficiency of appliance, improvement in the electricity grid generation. We called it electricity grid evolution. We applied all these 3 mitigation solutions to all buildings, existing buildings as well as new buildings. And we had the other 3 mitigation solutions that were applied just on new buildings. Improvement in the thermal insulation, improvement in the HVAC systems, also improvement in the embodied impacts of buildings. And then we had 3 different scenarios. The first scenario was the evaluating the GHG emission based on 2016. We called it no change scenario. The second scenario was projected improvement. This is based on the projected improvement in different databases. So, and we had also ambitious improvement, which is more aggressive compared to projected improvement. The main difference between projected and ambitious improvement is in the timeline of the application of these improvements. For example, in projected improvement, we start applying the improvement in 2016, and we will finish all different, applying all different mitigation solutions in 2045. In the ambitious improvement, we'll start in 2016, but we will finish 100% of application in 2035. Okay, this is our main graph, similar to the New York Times graph that I showed at the beginning of my presentation. So this is the historical database for GHG emission from the building sector in the US. In 2016, so we'll have 1.75 gigatons of CO2 emission, which is equal to 27% of the total US GHG emission. So if we consider the GHG emission from industry, GHG emission from transportation, GHG emission from building, is 27% of the total GHG emission. The first scenario, the first mitigation solution was electricity grid evolution. Then the second one was concrete production. So here we just consider different mitigation solution in order to reduce the impact of concrete in buildings. It's just about concrete. So concrete production. The third one is improvement in the appliances, improvement in the efficiency of lighting, improvement in the efficiency of HVAC, improvement in the efficiency of thermal insulation, and then improvement in carbon uptake after concrete disposal. So we consider also concrete disposal and also carbon uptake after concrete disposal. So if we just consider the projected improvement, we can have 47% GHG reduction in 2050 compared to 2016 levels. If we consider ambitious improvements, which are more aggressive compared to projected improvement, this reduction will be 56% compared to 2016 levels. And this amount of reduction will be around 1 gigaton of GHG. And it's interesting to know that this amount equals to almost 30% of the total reduction expected under Paris Agreement. So, and we believe that it's a kind of, huge reduction compared to other, mitigation solutions in other sectors. And as you can see here, single family buildings as well as warehouses and healthcare systems are the most important contributor to the total GHG emission in the building sector in ambitious improvement scenario. Okay, I talked about the annual GHG emission in the US. So this is about the cumulative GHG emission over 34 years from 2016 to 2050. So if we continue to build new buildings, if we continue to operate buildings similar to 2016 level, after 34 years, the total GHG emission will be around 62 gigatons in 34 years. So, but if we apply different mitigation solutions that I introduced in my previous slides, after 34 years, in 2050, the total GHG emission will be around 40 gigatons, and we will have 22 gigatons reduction in the GHG emission, which is a significant reduction based on different mitigation solutions. Okay. In the left-hand side, you will see two different maps, blue maps. The first one is for grid emissions, kilogram CO2 per kilowatt hour in 2016 at different counties, at county level in the US. And the other one is the grid emission in 2050. So you will see that the most important changes happen in Midwest area, in Missouri, in Illinois, also in Midwest area. And in the right-hand side, in the green map, you will see the total saving after applying those 6 mitigation solutions in different counties in the US per square footage. So you will see that still, so in Midwest, in those areas will have the highest savings after applying those mitigation solutions. It means that we have a strong correlation between the map in the electricity grid evolution, also in total savings in the US. So, and it means that the electricity grid evolution is the driving the GHG reduction in the US. Okay, I talked about the amount of GHG reduction, and this graph shows the cost of GHG reduction. So, and this graph shows the cumulative mitigation costs for one building, 1,000 square feet building over 34 years. So it shows that not only you will get saving in the GHG reduction, also will get saving in the amount of dollar that you will spend in that building in 34 years. Actually, we can save almost $865 over 34 years by applying those mitigation solutions. So it means that when we apply those mitigation solutions, we can get benefit from applying those mitigation solutions. And this graph is abatement cost graph. It's dollar per ton CO2. You will see that, for example, after applying those mitigation solutions for lighting and appliances, we can get benefit from applying those mitigation solutions. But for electricity grid evolution, for carbon capture, utilization and storage, and also for carbon uptake, we need to spend money in order to reduce the GHG. So we will see different costs regarding the different mitigation solutions in the US for the building sector here. Okay, so here we just wanted to focus more on the embodied emissions in the US. We had 4 different scenarios regarding the embodied impacts of concrete. We just focused on concrete in the buildings. So the first scenario was just applying low carbon binders, just applying supplementary cementitious materials. The second scenario was applying low carbon binders plus applying carbon capture storage in cement plants. Also, the third scenario is applying low carbon binders and applying carbon capture utilization in synthetic aggregates in the US in different cement plants. And also in the last scenario, so we assume that if we apply low carbon binders, if we apply CCU, and also if we apply CCS, we will have finally a concrete without any emission, with 0 kilogram emission. So that's the goal of the different mitigation solutions for the embodied impact. Actually, regarding the synthetic aggregates, which has a huge impact on the embodied impact, so we can find a couple of companies in Europe and US which are currently working on this carbon capture utilization in synthetic aggregates. So, and we got our assumption based on those plants and based on those processes for CCU in cement systems, in concrete systems. Okay, based on these mitigation solutions, if we apply those scenarios in a single family buildings, for example, in Chicago, we will see the impact. So in the left-hand side graph, we will see that if we have a wood frame building, we still have 31% of the GHG emission coming from concrete and mortar, mostly from the foundation. And also, if we have a concrete frame building, we will have 40% of the GHG emissions coming from concrete and mortar. So if we apply those mitigation solutions, we'll see that at the end of the process, we'll have concrete frame buildings with lower impact compared to wood frame buildings. Okay. And this slide is showing the results regarding the new buildings in the US. So in the bar charts, you will see that, for example, in 2016, the blue bar represents the amount of embodied impact coming from new buildings constructed just in 2016. The yellow bar in 2016 represents the use phase just coming the newly constructed buildings in 2016. But in 2018, if you look at this graph, the blue bar, again, is the embodied impact just from a newly constructed building in 2018. But the yellow bar represents the use phase coming from newly constructed building in 2016, 2017, and 2018. So considering this trend in 2050, the blue bar represents the embodied impact just for new buildings in 2050, and the yellow bar represents the total operational impact, use impact from buildings constructed from 2016 to 2050 in 34 years. Based on this graph, so we'll see that almost 23% of the total GHG emission is coming from the embodied impact and from materials production. And if you look at the donut chart here, we'll see that out of the 77% contribution of the operational impact, 45% is coming from the appliances, 20% coming from lighting, and just 12% from HVAC systems. And if you look at the right-hand side here, so we'll see that the total cumulative emission will be around 11.1 gigatons of CO2 just for new buildings constructed from 2016 to 2050. Key takeaways, the first one is that mitigation strategies can reduce up to 1 gigaton of GHGs, equal to 30% of the total reduction expected under Paris Agreement. Number two, is that electricity grid evolution from 2016 to 2050 leads to the highest GHG reduction. And the electricity grid evolution is driving the GHG reduction in the whole US, in the building sector. The third one is by applying more aggressive strategies. We called it ambitious improvements. We can save up to 22 gigatons of CO2 over 34 years. And the last one is that embodied impacts contribute to 23% of the total cumulative GHG emissions over 34 years in just new buildings in the US. Thank you so much for your attention, and I would be glad to answer any question about this presentation.